Okay, so now we are going to look at this problem. You might remember from the previous video, the board probably looked a little bit different. I had to teach, but I was able to redraw these characteristics. And so I just want to remind you that we have a situation here where we have these intersecting characteristics. So over here, according to the blue characteristics, if you're on the blue characteristic, the solution is 2 there. If you're on a purple characteristic, the solution is 1 there. But in this wedge right here, we have a problem. Within this wedge here, every point is going to be on 2 characteristics. So what is the value of the solution at such a point? So in this range, so if we're over here or if we're over here, if we're not in this wedge right here, there really is no ambiguity. The solution is either 2 there or 1 there. The ambiguity is in this wedge right here. So let me erase these characteristics because we don't know what the solution is in this wedge. And I can't remember if I said this in the first video or not, but the issue is opposite from what we saw last week. What we saw last week with these conditions flipped, with a 1 there and a 2 there, in this wedge right here, there were no characteristics. But now in this wedge, every point is going to lie on 2 characteristics. So we have to figure out what's going to happen in this wedge right here. Well, something has to happen. So again, if we imagine that U is the velocity of a gas or some other fluid, and we start with a velocity 2 here and a velocity of 1 here, something is going to happen as time progresses. And so we need to figure out what that something is. And so if we think about clearly what's going to happen, there's probably going to be some sort of discontinuity where the velocity 2 fluid catches up with the velocity 1 fluid, and there's going to be a discontinuity there. So we're going to assume that there's a discontinuity here because this kind of makes sense as what should happen. And so this black line here, this black curve here, let me see if I'm going to draw this a little bit differently. It's not going to look anything like what I have now. So let's say this is the black curve here. This is the point of discontinuity. To the left of the discontinuity, U is going to be given by the blue characteristics, and to the right of the discontinuity, U is going to be given by the purple characteristics. So it'll look something like this. The diagram will look something like this. Okay, except you'll see we're not going to have a curve that looks like this. Okay, and then, if maybe the shock looks like this. Okay, so this black curve is called the shock, and it has parameterization x sub s of t, t. Now this s right here has nothing to do with the s from the system of differential equations that I had written right there. That s means shock. The idea is that this is a shock wave. To the left of the shock, U is going to be equal to 2. To the right, U is going to be equal to 1. So there's this discontinuity that is propagating. And we want to understand how that discontinuity propagates. Okay, so essentially the only thing there is to do in this problem at this point is to find out the location or to find out the parameterization for this shock right here. Because we know to the left of the shock, the solution is going to be equal to 2, and to the right of the shock, U is going to be equal to 1. We just need a formula for that shock. Now to do that, we're going to have to write this equation in conservative form. So remember, we can write this as the t derivative of U plus the x derivative of U squared over 2 equals 0. Because if I use the chain rule here, I'm going to get the derivative of U squared over 2, which is U, times the x derivative of U. Okay, but this is what I want to say slightly more generally. Instead of U squared over 2, we're just going to look at a general f of U. So we've been looking at conservative equations like this for the entire semester. Even when we talked about the diffusion equation, we came up with an equation like this, and then later realized that f of U, the flux, is going to be equal to something like minus the gradient of U. So these sorts of equations we looked at all semester, and to be able to resolve this ambiguity here in this wedge, we're going to need to have it in this form. So here's what the plan is going to be. We're going to look, we're going to pick a generic value of t, and look at a very short x interval. So we're going to look at the integral, we're going to call it q of t, is going to be the integral from xs of t minus epsilon to xs of t plus epsilon. Now, it's going to be cumbersome if I write this t all the time. So xs, it should say xs of t, but instead of writing that explicitly, I'm not going to write that because it gets too cumbersome. So this means xs of t and then minus epsilon. Now I have plus epsilon u of xt dx. And essentially what we want to show here is that as epsilon goes to 0, this quantity should be conserved. So what we want to say, like the physical thing that tells us how we should resolve this discontinuity here, is that we want u to be conserved even over the shock. So in other words, if we look just a little bit to the right of the shock and a little bit to the left of the shock, the integral of u over that should remain constant. So what's going to happen, we're going to do this integral. We want it to be constant for all values of t, but because this is just like a generic epsilon, we don't know if this is actually going to be constant for all values of t, but we do know as epsilon goes to 0, this should be constant. So what we're going to do is we're going to parameterize this with epsilon. We're going to compute this in terms of epsilon. We're going to take the limit as epsilon goes to 0, and from that we're going to be able to figure out what x sub s should be. Okay, actually we're going to figure out what x s prime should be. Okay, so I just want to emphasize, I just want to remind you, or to explain a little bit more about what's going on here. If you remember when we looked at the traffic equation, I said imagine you are in a car at position x naught. The number of cars between you and the car at position 0 should remain constant as time goes on. And then we came up with a formula for the location of the car that starts at x naught, how that evolves over time. And we said for these two cars, between these two cars, there's always going to be the same number of cars under the assumptions for the traffic equation. In reality, we would like to do something like that here. We would like to be able to, take that point, and kind of track that as time goes on, and maybe it'll get a little bit bigger, a little bit longer. And then between those two points, we know we're always going to have the same amount of stuff, whatever u here is representing. But it's too generic. We can't come up with a formula in the same way that we did for cars. So instead, the next best thing is just to say, well, okay, if epsilon is very small, q epsilon of t should be basically constant, okay? And now the way we say that mathematically is we're going to take the limit as epsilon goes to 0. All right, so in other words, not really the limit of this, but we're going to take the derivative. And now this limit as epsilon goes to 0 should be equal to 0. We're saying that if this derivative is constant, if the derivative of q is constant, we're saying that this quantity is conserved. Okay, so we're saying that this is equal to 0. Now what we want to do is we want to put the derivative on the inside. But there's two issues. The first issue is that the limits here depend on t. And the second issue is that this is technically an improper integral. It's an improper integral because we are integrating over a discontinuity. So you have to integrate from xs minus epsilon to xs, and then from xs to xs plus epsilon. So altogether, this is going to be the derivative with respect to t, the integral of xs minus epsilon to xs u plus the derivative from xs to xs plus epsilon u dx. Okay, you just have to split it up because we have the discontinuity. Okay, like if you integrate, x from 0 to 1, and then 1 plus x from 1 to 2, you can't just do the antiderivative of 1 plus x minus the antiderivative of 1 plus x at 2 minus the antiderivative of x at 0. You have to split it up, and that's exactly what we're doing here. Okay, but now I want to be able to move the derivative on the inside here. But if I want to do that, I have to use the Leibniz rule because these bounds here depend on t. So what this integral here, just this integral, what that's going to be equal to is it's going to be xs prime, that is the derivative of the top bound, times the integrand, which is u, evaluated there, so xst, minus the derivative of this, which is going to be xs prime, times u, the integrand evaluated there, xs minus epsilon, and then it's going to be plus the t derivative of the integral. So plus the integral xs minus epsilon to xs times the t derivative of u. Okay, so that's what the first integral is equal to. And then we're going to get something similar for the second integral. Okay, the second integral, kneel down here, it's going to be the derivative of that with respect to t. So it's going to be xs prime times u evaluated at that point. So xs plus epsilon t minus xs prime times u evaluated there. So u of xs comma t, and then plus the t derivative of the integral. xs to xs plus epsilon, the t derivative of u. All of this stuff down here, I'm going to write up here in just a minute. Okay, now notice what's going to happen here. Right here, I have an xs prime, u of xs, and over here, I have a minus. So those two terms are going to cancel. So when that happens, what this is equal to here, I didn't have my phone on silent, sorry. So we'll have the blue part. So we're going to have xs prime. Well, xs prime is on both of them. Sorry, I'm trying to color code this as best as I can. So we're going to have xs prime xs prime times this, so u of xs plus epsilon, like that, and then minus xs prime times u of xs, sorry, there should be a comma t there, so u of xs minus epsilon, comma t, like that. And then I'm going to write the two integrals, so it's going to be plus the integral from xs minus epsilon to xs times the t derivative of u plus the integral from xs to xs plus epsilon times the t derivative of u. And sorry, both of these integrals are with respect to dx. Like that. Okay, so now that's what we have here. So this is xs of t times this plus those two integrals. Okay. So now if I come down here, I'm going to come all the way over here to the left because I'm going to need the room. So we're going to have xs prime times u of x sub s plus epsilon comma t minus u of xs minus epsilon comma t. Okay, so I'll write the integrals in just a second, but let me just tell you what I'm writing here. U of xs minus epsilon. I'm looking at u to the left-hand side of the chalk, so I'm evaluating u at that point. And u of xs plus epsilon, I'm evaluating u at that point. Okay, so what we have here, this right here, u of xs plus epsilon minus u of xs minus epsilon, is just the value of u here minus the value of u there. Okay, so the color coding is consistent with what I have up there as well. Okay, so now what we're going to do is the t derivative of u, if I look at the equation here, the t derivative of u is equal to minus the x derivative of f of u. So this is going to be minus xs minus epsilon 2xs times the x derivative of f of u. Okay, I'm going to give myself enough room here, and I can replace this with something similar. There's going to be the integral from xs to xs plus epsilon times the x derivative of f of u. Now what I'm going to do is I'm going to use the fundamental theorem of calculus. So it's the derivative, I'm doing the integral with respect to x of the x derivative of f of u. So forgetting about the minus sign, it's going to be f of u evaluated here minus f of u evaluated there. Okay, or with the minus sign, it's going to be f of u evaluated there plus f of u evaluated there. So we're going to get minus f of u of xs comma t minus f of u of xs minus epsilon comma t. Plus. It's a minus, so it's going to be a plus there. And I'm going to have something similar over here. So I'll kneel down again. So this is going to be f of u of xs plus epsilon comma t minus f of u of xs comma t. And it's minus a minus, so this is a plus. Okay, but now look what happens. We have a minus f of xs, so that's going to go. That's going to pair off with this. So those are going to go away, and we're just going to have this plus f of xs minus epsilon, and then the plus epsilon. Okay, so what we're going to have then, this is going to be equal to minus that one. So f of u of xs plus epsilon comma t, and then minus the blue one, which is going to be f of u of xs minus epsilon comma t, like this. Step out of the way here. Okay, so overall what this equation reads is q epsilon prime is equal to xs prime times u of xs plus epsilon t minus uxs minus epsilon t minus this thing here. And yeah, that's right. Okay, so in other words, I can solve this for xs. So I'm going to do that now. I'm going to solve, if I imagine the q epsilon prime t being here, I'm going to solve this for x sub s prime. And when I do that, I'm going to get the following. So now I have room, so I will write the xs prime of t. So this is going to be equal to q prime epsilon of t divided by the thing that is multiplying xs prime down here. So it's going to be u of xs plus epsilon comma t minus u of xs minus epsilon comma t. Same color coding scheme. And then plus, if I add that to both sides, we're going to get f u of xs plus epsilon comma t minus f of u of excess minus epsilon comma t. And then all of this is going to be divided by the same thing that I have over here. So u of excess plus epsilon comma t minus u of excess minus epsilon comma t, like this. All right. So now erase this. And I want to take the limit of this as epsilon goes to 0. So I want to take the limit as epsilon goes to 0. So I'm going to do that now, and I'm going to replace it with stuff. So u of excess plus epsilon as epsilon goes to 0. That is just the limit as that's just the limit from this direction going to the shock. In other words, it's going to be the value of the solution directly to the right of the shock. So I'm going to call this u sub r. As epsilon goes to 0, that's what I get. That's going to be u sub r. Now, technically, in more general situations, u sub r is not just going to be equal to here, u sub r is equal to 1. In more general situations, ur depends on x and t, so I really should be writing like of x comma t, but I'm not going to do that now just because it makes the notation too heavy. And similarly, u of excess minus epsilon comma t, as epsilon goes to 0, we're doing the limit that way. In other words, this is just the value of the solution directly to the left. Now, we're assuming, in this problem, we're assuming that there's a jump discontinuity. Okay, so for this problem, u is equal to 2 on the left and 1 on the right. In general, that's not going to be the case. But we are assuming there's a jump discontinuity. We're assuming there's a discontinuity across the shock here, in which case ur and ul are not going to be equal to each other. So what's going to happen, as epsilon goes to 0, the denominator is just going to go to whatever ur minus ul is. Okay, it's not going to be equal, ur minus ul is not equal to 0. But if the quantity, if u is conserved across the shock, this should go to 0. So we're going to have 0. So we have 0 over something that's not 0. So this term is equal to 0 as epsilon goes to 0. Now over here, what's going to happen? Well, down here, we're just going to have ur minus ul again. Here we're going to have ur minus ul. And now if u is a continuous function, this goes to ur. So this is going to go to f of ur. And since we're taking derivatives of f, it's safe to assume that it's continuous. F of ur, and over here it's going to be minus f of ul. Okay, so what this tells us then is the derivative of the shock. In other words, xs prime of t. If this is the parameterization, xs prime of t, that is the derivative of its x position, right? The shock is traveling down the pipe. Xs of t is its location down the pipe. This is the derivative of the x location. It's given by f to the right of the shock over f to the left of the shock divided by the solution to the right of the shock minus the solution to the left of the shock. And this has a formula, or not formula, it has a notation. So x s prime is equal to bracket f over bracket u. And this notation just means f is the value to the left of the shock minus the value to the right of the shock. U bracket is a u to the left of the shock minus u to the right of the shock. Or sorry, I got it backwards. U to the right minus u to the left. In other words, it's just the jump of f across the shock, and this is just the jump of u across the shock. And again, since we're assuming there's a discontinuity, we're assuming that these values are not equal to 0. Okay. So what we're going to have now, we're assuming the denominator of these is not equal to 0. Okay, so this is sort of the generic problem. We have xs prime is equal to the jump in F over the jump in U of the shock. That's going to be basically it for this video. This is xs prime is equal to this quantity here. For a given F and a given U, we have to compute what that is. So in the next video, I'm going to look at this function, show you what F is, or I'm going to look at this problem, show you what F is, we're going to compute the shock, and we're going to compute the derivative of the shock, and from that we can compute xs of t, and from that we'll be able to compute the rest of the solution. But that's it for this video. Oh, actually, one other thing. This condition that we have here, or this quantity right here, is called the Rankine-Hugoniot condition. This is embarrassing that I can't get this right. This is like when I teach this class, this is my most anxiety-provoking day because I cannot say these names. So this is Rankine. This is a Scottish mathematician, engineer, etc. This is a French, same thing. Hugoniot. Okay, Rankine-Hugoniot conditions. And so I will often abbreviate this as just RH. Like, let's use RH to find the shock velocity. For example, is how I might say this. Okay, that's it for this video. That's a lot. Make sure that you understand where this shock comes from, but also just make sure you understand this formula. And that'll probably not happen until we actually apply it in the